Today I would like to present our project, which is a distributed campus library system for a university environment such as UNIZA. This system allows students and staff to search for book, check book availability, and perform borrowing and returning transaction. Unlike a traditional library system that use only one server, our system use multiply distribute server nodes location at different faculty or branch. The system apply three important distribute system concepts, which are processes and thread naming system and replicate data consistency. This concept have improved performance, reliability, and data and across the library system. For the problem statement, there are several problems identified in the current library system. First is many library processes are still done manually or using. For the problem statement, there are several problems identified in the current library system. First is many library processes are still done manually or using semi-automated system. This make the process slow and inefficient when the number of users increase. Second, it is difficult to manage data across multiple servers and ensure all information is always up to date, especially in a distributed environment. Third, most systems do not support real-time synchronization between servers. This can lead to inconsistent data, such as incorrect book availability or duplicate records. Lastly is centralized systems have limited scalability, so system performance may decrease when there are many users increasing the system at the same time. For the system overview, our distributed library system consists of three server nodes. Node A is the main library server, while Node B and Node C are faculty replica server. Each node store a copy of the same book database to improve availability and reliability. When three updates such as borrowing, returning, or adding books, the information is shared between all nodes using message passing to keep the data consistent. This system also improves scalability because more nodes can be added in the future without affecting the whole system. For main components, the system has three main components. First is request handler thread. This allows the system to handle multiple user requests at the same time, improving performance and reducing waiting time. Second is the local state manager. Each node has its own local database, which allows faster access and avoid a single point of failure. Third is the replica manager and network socket. These components are responsible for sending and receiving updates between nodes to make sure all data is always synchronized.
So today I would like to share about trade model developer. So the trade model developer will have three parts, which is dynamic trade management, synchronized execution barrier, decentralized local count decrement. So for dynamic trade management, replace heavy memory consuming process creation. The system dynamically allocate lightweight worker to each form. a managed trade pool to handle hundreds of concurrent student borrowing requests without causing server crash or resources exhaustion. Next, synchronous execution barrier. Implement the synchronous keyword to establish mutual execution within the system. This critical security layer forces student trades to queue when accessing the same book, effectively limiting race condition and preventing data corruption. Lastly, for decentralized local power deployment, eventually modification occur directly within the node accelerated memory viewing. The book count is safely reduced inside the critical section before the system triggers asynchronous background application to peer nodes. To prevent race condition and data corruption, I implement a synchronous migration like this based on this coding. Public synchronous void borrow book if local book more than 0 and local book count. So now I will be explain the process and communication model for our system. So next, as you can see based on this figure, when student requests come in, our target server does not create heavy new processes. Instead, we use manager pool via Java code executor service. This allows the server to handle multiple student requests dynamically without overload the system. So now, moving the most, so now we move the most critical part, which is the yellow box. The yellow box, the synchronous execution. When many students try to borrow the extract same book as the extract time the same time, we raise a facing raise condition. For prevent this condition, we implement a synchronous execution barrier as I show the coding below before. The diagram I apply synchronous keyword. This acts as a straight lock to ensure mutual execution, meaning only one thread can process the book borrowing at any given time. Last part, which is local count decrement. Once the access is safely granted, the system performs the local count decrement. It safely reduces the book inventory in local database first before the background application process begins. So next, I will discuss the architecture trade-off between trade-based and process-based design. Okay, so as you can see this table, our evaluation clearly show that the trade-based architecture is significantly more efficient. So because trades share the exact same address space within the node, it results in extremely low memory overhead and near asynchronous communication speed compared to the heavy OS intervention required by a process-based design. So we know acknowledge a trade-off here as started in the fourth isolation row. A tree-based design is more vulnerable because tree share crash risk, whereas processing fail independently. However, referring to our engineering at the bottom, we make calculated choice. We prioritize high scalability and low latency to support the massive peak hour for unitized library system. Therefore, the trade-based approach remains of our most optimal choice. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I'm Fatima Rabatino Asman and my metric number is 083198 and I'm the memory system architect for this project. So in a multiplicity environment like our campus network,
A reliable naming subsystem is vital to locate distributed resources seamlessly. So to achieve this, our system implement a hybrid approach combining both structured and flat naming. For the user-facing interface, we selected structured naming using a human-readable dot-separated convention, especially for Uniza.me, Uniza.fyk, and Uniza.fpp. So this abstract the complex underlying IP and port configuration away from the student. On the other hand, we utilize flat naming exclusively for written subsystem tasks. This identify consists of flat alphanumeric bit string which are highly flexible and secure for machine-to-machine validation. Moving on to the actual technical deployment, the core logic is encapsulated within the naming service class. To grant total tweet safety and the intense operation, both routing registries are instantiated using concurrent hash map. So this implementation design ensures fine-grained locking, allowing the network to handle concurrent search smoothly. So looking at the code structure, the resolve structured method handles incoming lookup by actively synchronizing the string using the split function with a dot delimiter. So this isolates the root authority from the local organizational context to discover the exact server's OK address. Meanwhile, the resolve flat method skips text parsing completely, executing a direct index query using the static node identifier for accelerated processing. Finally, this is how architecture directly support our group integrated processes. So during scenario B, which evaluates high concurrency, our node is raised within 100 concurrent client tweets. Because of our tweet safe mapping, the naming registry resolve addresses flawlessly without triggering lookup delays or race condition. More importantly, in scenario C, which simulate node failure and recovery, node C abruptly drop offline and regions later. When it recovers, the log manager must instantly replay missing transaction update. So instead of wasting CPU cycle parsing hierarchical strings, the system involves resolve flag to target node C directly using its flag identifier. So this bypasses steps manipulating latency, allowing the system to achieve eventual consistency immediately without losing data.
For scenario A, normal load. In scenario A, the system is tested under normal condition. We simulate 10 client threads performing around 100 search and borrowing operation. The purpose is to check system stability, response time, and communication between nodes. The expected result is that the system can respond quickly and maintain correct data across all nodes. For scenario B, high concurrency. In scenario B, the system is tested under heavy load. We simulate 100 client threads, accessing the system at the same time, performing search, reservation, and borrowing operation. The purpose is to test system capability and performs under high user demand. The system also should still work efficiently without major delay or failure. Scenario C, node failure and recovery. In scenario C, we test system reliability Node C is disconnected during an active transaction while it is offline. The other nodes continue to operate normally. When node C connect, the system automatically synchronizes missing data using a recovery process. This shows that the system is fault tolerant and can recover without losing important information.
Assalamualaikum warahmatullahi wabarakatuh. Today, I would like to talk about the replication and consistency strategy. For this project strategy, the storage approach is utilize a decentralized replication state storage model where each library node independently tracks its own book inventory in local memory. Dynamic multi-model design, the system is engineered to support two distinct consistency models to adapt to varying operational workloads rather than being restricted to a single strategy. For sequential consistency protocol, it prioritizes strict data correctness via synchronous blocking operation to ensure all nodes sequence replication identically before releasing the log. For eventual consistency protocol, it prioritizes high availability and low latency via asynchronous background thread splitting to handle simulated network delays gracefully. The modular management component, it centralizes all synchronization logic into a dedicated replication manager, cleanly decoupling peer node coordination from core to node processes. For scenario A, we are analyzing the impact of sequential consistency under a normal workload of 10 concurrent threads. As shown in the console log, where 10 transactions hit node A, the system enforces a strict synchronous and blocking protocol. This means the system ensures that book updates are immediately propagated to node B and node C at the same millisecond. As the result, final replication counter shows a perfect 10/10 across all nodes, guaranteeing absolute data correctness with zero stale data. Moving on to scenario B, we stress tested the system using a high concurrency workload of 100 concurrent threads at node B. To maximize availability, the system throughput, we switched to eventual consistency using asynchronous thread splitting. In the log, you can see an immediate check shows 0 transaction replicated to node A due to a simulated 2-second network latency. This is the stale data we got. However, once the latency clears, our background threads achieve eventual convergence, successfully bringing the final replication state to a complete 100/100 for both node A and node C. Finally, scenario C demonstrated our system fault tolerance during a network disruption. When node C abruptly goes offline, our system isolates the failure path to prevent a complete crash. The log manager component automatically intercepts the issue and queue to 2 missed transactions from node A into memory. As soon as node C recovers and goes back to online, a resynchronization event triggers, replaying the stored logs to successfully restore node C back to a consistent state without any data loss or manual intervention.
Assalamualaikum, my name is Nushari Diani binti Abdul Syahadat. I am the system integrator and tester for this project. I will present our empirical evaluation results starting with the quantitative verification metric on this slide. We evaluated our distributed network across 3 distinct environments. Scenario A, sequential control, tested with 10 threads using our hierarchical engines, achieving 100% immediate consistency with 0 millisecond converse latency under a synchronized booking loop. Scenario B, high stress concurrency, scale up to 100 threads, shifting to asynchronized workers, which require to 1500 to 2000 millisecond converse window. Scenario C, for interception, executed during an active network partition, maintaining 33.3% initial consistency across the surviving links. acoustically across all heavy simulation tests. Our architecture achieved 0% data loss and 0 packet attrition, provide the overall structural integrity of our system. On this slide, let's analyze the engineering traits of between strong and eventual consistency. In scenario A, we enforce a synchronized tight coupling model. The metric shows an instant flawless 10/10 transaction seems to node B and node C. This is achieved by strict serialization, where the calling worker thread is blocked until cross-network acknowledgement completes. The trade-off is clear. It eliminates data race condition but introduces massive latency overhead under high multi-user traffic. To mitigate this, scenario B utilizes unsynchronized high-load convergence when 100 threads concurrently hit the node. Replication tasks are handed off to background worker pipelines, unblocking client execution immediately. While we count a temporary mid-transit stage difference due to the 2000 millisecond network delay, or replica stage successfully convert to a perfect 100/100 transaction mesh without a single deadlock. Finally, this slide demonstrates my primary component focus. Scenario C, fork containment and log recovery. To test network partition risk lines, we forcefully isolate node C's network link during active write operation. Our fork containment layer successfully prevents cascading thread or system crashes. Active node A and node B, continue processing transaction normally, with local inventories dropping down smoothly from 89, 88 to 87 books. For dynamic mutation interception, the two misses transaction payloads mean for the isolate node C were automatically intercepted and cached inside a resilience offline queue. Once node C rejoined the network, our flat address replay recovery kicked in. To maximize recovery speed, the system bypassed hierarchical passing and utilized direct flat addressing vector, such as the unique hash A1 identifier for rapid target mapping. The log manager replayed the two misses update sequentially, bringing node C exactly back to a perfect match of 87 books with 0 data loss. This proves our system is robustly designed to meet high reliability and data integrity level during unexpected hardware or link failures. That's all from me. Thank you.
In conclusion, this project shows how distributed system concept can be applied in real library system. Other than that, process and thread help handle multiply user efficiently. The naming system help locate resources easily. Data replication and consistency ensure that all nodes have the same update information. Overall, this system is scalable, reliable, and fault tolerant. It also improves performance compared to a traditional centralized system. Thank you.